And once again, we are back together. All right, and this time we are going to be learning how to determine the limiting reagent, right? This time using chemistry. You'll remember that in our previous video, we were using our cheese and bread model to make a sandwich, right? So if you haven't subscribed, do the right thing and be a part of us. All right, and we'll be happy to welcome you into the family. And if you should ever need assistance in maths and science, you're more than welcome to get in touch with us. All the details that you need will be in the description of this video. All right, now firstly, let's talk about determining the number of moles. Now in chemistry, the first thing that you should remember is that we always work with moles. Now, there are different ways to get there, right? So firstly, you have to know how to determine moles when given the mass, okay? You have to know how to determine moles when you are given the volume of a substance, okay? That's obviously if we have gases, but we also need to know how to determine moles when we are given, let's say, the number of particles, right? Now, particles could be atoms, it could be molecules. So when given particles, all right? And the last one is also determining the number of moles when we are given concentration. And I'm going to give you kind of a roadmap that we always use, right? Now, let's talk about this first. So when I'm given mass, right, the formula that we always use is number of moles is mass divided by the molar mass. Now, ladies and gents, it is very crucial for us to know how to determine the molar mass. So we would have been given the mass, and this would be in grams, okay? And in this case, the molar mass, this we get from the periodic table. Okay, so from our periodic table, and what we do use there, of course, this is given to us in grams per mole, right? So we actually work out the number of moles using mass divided by molar mass when we are given the mass. Now let's talk a little bit. How do we determine the molar mass? So it's easy. When we've got an atom, right? Say, for instance, if I give you nitrogen, so it means that you've got 2 atoms of nitrogen. So we'll go to our periodic table, right? We've got it right there. Okay, you'll see there that nitrogen has a molar mass. So that's the number right at the bottom. So nitrogen has a molar mass of 14. So ladies and gents, please, I want you to note. So to determine the molar mass of nitrogen, right, all we're going to do is say, well, we've got 2 atoms of nitrogen and we multiply that by the molar mass, which is 14. And so that means that the molar mass would be 28 grams per mole, right? So for argument's sake, if I had given you, let's just say, let's say 15 grams of nitrogen, right? So how I would get the number of moles is that I would say, well, the number of moles would be mass divided by the molar mass. And so the mass would be 15 grams, okay, what I'm given, right, divided by 28 grams per mole for nitrogen, because we know that it is a diatomic gas, right? So that would say 15 divided by 28, and we'll get whatever answer that would get in moles, right? Okay, if you want us to calculate it, then that's 15 divided by 28, and I get 0.5, let's say 0.54, right? If we round it off to 2 decimal places, right? So that's 0.54 moles of nitrogen that you would get. Now, of course, calculating the molar mass can be slightly challenging depending on, the molar mass. However, I do want to give you a warning, and I will give you the warning a little bit later. So let's do this just for, practice, right? If I give you, let's say, lead nitrate, something like this, how would I calculate the molar mass of lead nitrate? Okay, and please don't be alarmed. This guy is called lead. Okay, even though it is actually written as PB, and this comes from in German, actually, it's actually plumbium, right? That's where plumbing comes from, right? And that's why that it's got the symbols PB, right? So in this case, how we're going to determine the molar mass? We'll say, well, the molar mass of lead nitrate. Now notice, ladies and gents, right, what do we have? We've got lead, we've got nitrogen, we've got oxygen, right? So we're going to look for lead in our periodic table, right? There it is over there. And you can see the molar mass is 207. Right, so we're going to say 207. And please remember, you do not multiply by the coefficient. And I'll tell you why I'm saying that in just a little while. Right, now notice we've got a 2 that is outside the bracket. So what I'm going to do is I'm going to put the 2 here and open a bracket, right? So that means that inside the bracket we've got nitrogen with 3 oxygen. So nitrogen, you'd see that's 14, right? And oxygen is 16, right? So in this case, which means we've got in the bracket 1 nitrogen, which is 14, plus we've got 3 oxygens, so that's 3 times 16. But all of that is multiplied by the 2, so let's calculate that quickly. So we're going to have 207 plus, that's 2 into 14 plus 3 times 16. And so that's what we get. That would be 331 grams per mole. That's how you would determine the molar mass of lead nitrate. Now, guys, of course, we can spend a bit of time. Sometimes you've got a substance that has got what we call waters of crystallization, right? So in this case, let's say H2SO4 times 10 H2O there. In fact, it's not times, with 10 H2O. So in this case, what we call this, we call it waters of crystallization, right? So how do we determine the molar mass in that case? So from the periodic table again, so I'm going to say the molar mass, we've got 2 hydrogens, right? Hydrogens has got a molar mass of 1. So you always multiply by the subscript in this case, right? The number at the bottom. So that would be 2 times 1 plus sulfur is 32. So this is plus 32 plus we've got oxygen, right? 4 of them. So that's 4 times 16, which is the molar mass for oxygen. You can check in your periodic table, right? So you add the waters of crystallization. So this would be plus 10 times. In this case, we've got 2 atoms of hydrogen, right? So that's 2 times 1 plus the oxygen, which is 16. So what we do is that we're going to calculate everything here. And notice, ladies and gents, that we are adding everything, right? So 2 times 1 plus 32 plus 4 times 16, right? So that's for the sulfuric acid. Plus, now I'm going to add the waters of crystallization. That's 10 times. I open the bracket. That's 2 times 1 plus 16. Right, so ladies and gents, that gives us 278 grams per mole. Okay, so that's how we'll calculate the molar mass of any substance. Now, guys, I want us to quickly talk about now converting from mass to moles, which we've just done. We said we use the formula number of moles is mass divided by the molar mass, right? So we'll take the mass there and divide that by the molar mass. Now, we're going to talk about how to determine the limiting reagent, right? So we need to be able to first convert from mass to moles. Now, I did say to you that sometimes we would be given volume, and that's why I have this table in front of me. So if we've got mass, we said that's mass divided by molar mass. But when we've got the volume, so to calculate the number of moles, we'll simply say number of moles is volume divided by the molar volume. And guys, I want you to note this molar volume will be given to you, right, for whatever temperature and pressure you have. So we know if we've got standard temperature and pressure, right, our molar volume will always be 22.4 cubic decimeter per mole, right? So that is what we would use. So we would be given the volume of, a gas, and we get the number of moles by taking that volume and dividing it by the molar volume. But if we've got particles, so we simply say number of moles is the number of particles. So if we're given atoms, right, or if we are given molecules, we will definitely say number of particles divided by Avogadro's constant. And guys, Avogadro's constant, you are also given that, right? So that's 6.023 multiplied by 10 raised to the exponent 23. And so that's the constant that we're going to use here. But of course, when we've got concentration, right, we know that concentration, right, is number of moles divided by volume. But if we want to find out what the number of moles are given concentration, we'll simply say number of moles is concentration times volume. Now note that concentration is used in moles per cubic decimeters. But of course, if you're following the American curriculum, we use molar there, right? Okay, and the volume is given to us in cubic decimeters, right? So if it's in cubic centimeters, we need to convert it to cubic decimeters. But of course, we'll treat that as we go along, right? Now, I want to talk about how to then determine the limiting reagent, right? So in this case, what we do is that the first thing we are going to do is we're going to determine number of moles. And I did say to you, we can be given the mass, right? And I've showed you, we can be given the volume, right? We can be given, we said concentration, right? Or in this case, we can be given the number of particles, right? Particles would be would be, atoms, as I said, or it could be molecules, right? So we convert that to moles first, right? So remember, in chemistry, we always work with moles. And so we are now going to use our stoichiometric ratio. And I'm going to show you how to use that. Okay, there it is. I'm writing ration instead, right? So we use our ratio, right, to determine, in this case, the moles. So what that helps us with is to now determine the moles of the other substance that we are looking for, right? And of course, sometimes they may say to us, calculate, let's say, the mass, the volume, or for whatever it is that we are given. And of course, we can convert it back from moles to mass, or to volume, or to concentration, or even to the number of particles, depending on what the question wants from us. Ladies and gents, if you note this roadmap, it will always help you to deal with stoichiometry. If I were to even mention acids and bases, if you understood this, right, acids and bases really becomes a breeze and a walk in the park, right? So ladies and gents, what I want us to do is to take a couple of examples and see how to apply this principle and how to determine the limiting reagent using, in this case, our roadmap. So I just pulled this off the internet, and it is freely available. Right, so they say to us, if I do this reaction, so we've got 2C6H10 plus 17O2, that's definitely a combustion reaction, right, giving us 12 carbon dioxide and 10 H2O. Now they say if I do this reaction with 35 grams of C6H10, so that's that's hexane, right? So in this case, well, hexane in this case, right? And 45 grams of oxygen, how many grams of carbon dioxide will be formed? Now, firstly, ladies and gents, I want us to note that we've got an amount of hexane that's given, right? So there it is over there, 35 grams. but they've also given us an amount of oxygen. So first we're going to have to determine which one will limit the extent of the reaction. Now, if you remember what I said, we always start, if we're given grams, we have to convert them to moles. So let's do that first. Let's calculate the number of moles, right, of C6H10, right? So this is going to be mass divided by the molar mass. Now, ladies and gents, remember, we said in this case we're going to have, well, we're given 35 grams. And so the molar mass, we've got 6 carbon atoms and 10 hydrogen atoms. Now, please, guys, this is the warning that I wanted to give to you. Please do not ever multiply when calculating the number of moles. Please do not ever multiply by the coefficient. I'll show you what we use the coefficient for, but you do not multiply by the coefficient to calculate the number of moles, right? So in this case, we've got number of moles. So how do we get the molar mass of C6H10? So that's going to be 6 multiplied by, the molar mass for carbon is 12, right? You can check in your periodic table, plus, in this case, the molar mass for hydrogen is 1, but we've got 10 hydrogens. Right, so in this case, that is it. Right, now let's try to calculate it quickly. So we've got 35 divided by, we said this is 6 times 12 plus 1 times 10, which is 10. Okay, so I get 0.4. Right, I'm going to round off in this case. I'm going to say this is 0.43, right? Just to make it easier for us. So that's 0.43 moles. So these are the number of moles of hexane that we are given, right? So this is what we have. We haven't yet calculated the limiting reagent. We don't know which one is the limiting reagent just yet. Okay. Now, ladies and gents, let me check. Given these number of moles, let's assume that hexane C6H10, right, was the limiting reagent. How many moles of carbon dioxide would I be able to produce, right? So whichever one would give me the least number of moles, then in that case, it should be the limiting reagent, right? So I'm going to say, now note, this is where now I use my stoichiometric ratios, right? So I'll say for every 2 moles of C6H10, H10, I get, or I produce 12 moles of carbon dioxide. That's according to the ratios that I have there, right? So how many moles, right? So for 0.43 moles, now note the same thing on the same side. So these were the moles of hexane, which is C6H10, right? For 0.43, how many moles of carbon dioxide am I going to produce? Okay, so I'm just going to use that as N. Right, so I cross multiply. Remember what I said to you, ladies and gents? When we cross multiply, we only take the coefficients, right? So 2 multiplied by N, that will give me 2N. And 0.43 times 12, that will give us, let's take that, 0.43 times 12, that gives us 5.16, right? So that will be 5.16. And so I'm going to divide both sides by 2. Okay, so in this case, I don't know why I removed that. 5.16 divided by 2, 2.58. So now please, I want you to listen very carefully, ladies and gents. Assuming that our hexane is our limiting reagent, right? It would actually produce 2.58 moles of oxygen. Now, here's what I want us to do. I want us to check, all right? we are now going to determine which one is the limiting reagent first, and whichever one is the limiting reagent will therefore dictate or determine how many moles of the products we find, right? But it would also determine how many moles of the other reactant are used, and as a result, how many would be in excess, right? So we just found out that if hexane, right, was the limiting reagent, so therefore we would be able to get, in this case, 2.58 moles of carbon dioxide. Right, now here's what I want us to do. Let's now determine the number of moles of oxygen, right? So I'm going to remove all of these, right? So the number of moles of oxygen that are given. Now we're given 45 grams of oxygen, right? Let's first convert that to moles. So that's mass divided by molar mass, right? So the mass of oxygen, 45. Now remember, oxygen is O2, so the molar mass is 16, but we've got 2 of them. Please, again, ladies and gents, do not make the mistake rather of using or multiplying by that 17, right? So it is 16, so divided by the molar mass, so that would be 16 multiplied by 2. Okay, so let's get that molar mass in this case. So that's 45. Let's get the number of moles rather. Divided by 16 times 2, which is 32. And so we get the number of moles of oxygen to be 1.4, well, let's just say 1.41 moles. Okay, right. Now, with the number of moles of oxygen that we have, how many moles, if oxygen was to be the limiting reagent, right, how many moles of carbon dioxide would we actually make? Right, so I'm going to do that again, right? Let me just use a different color. So assume that oxygen is the limiting reagent. So for every 17 moles of oxygen, I produce 12 of carbon dioxide. So for 17 moles of oxygen, I would produce 12 moles of carbon dioxide. So the question is, if I'm going to use all the 1.41 moles of oxygen, right, how many moles of carbon dioxide would we produce? Now let's cross multiply again. 17 multiplied by n, right? That would give me 17n. And 1.41 times 12, right? Let's take that. So 1.41 multiplied by 12. So that gives us 16.92. And we're going to divide both sides by 17, right? So this gives us, I don't know why I keep removing the answer there. Okay, so that's 16.92 divided by 17, right? And this gives us the number of moles of carbon dioxide that would form would be 0.9, well, let's just say let's say 1, right? Okay, so we would actually get 1 mole. Now, guys, I want you to please listen very carefully, right? If we were going to be able to utilize all of the, the hexane, we would obtain 2.58 moles. Of course, assuming that the number of moles of oxygen would be sufficient, right? But in this case, we realize with oxygen can only get us to 1 mole, right, of carbon dioxide. We would like to produce more, but this guy says, well, I cannot produce any more than 1 mole. So can you see that the number of moles of carbon dioxide that we produce is less when we use actually oxygen as our limiting reagent, even though seemingly it had more grams, right? But it gave us a limited number in terms of the number of moles. Now, ladies and gents, I want you guys to please note this, right? So, what does this mean? It means, therefore, that the one that gives me the lesser moles of carbon dioxide is the one that will be the limiting reagent. Okay, so let's do this. Okay, I'm going to remove the other calculation, just for the sake of having space. So, which means now that oxygen is my limiting reagent. Okay, so please remember that oxygen is our limiting reagent. Why? Because it gives us lesser products. Okay, so they wanted us to find out, okay, how many grams of carbon dioxide will be formed. So we just found out, ladies and gents, that the number of moles, right, of oxygen, right, we actually calculated that. We said that was 45. Remember how we got to that? We said that was 45 divided by, remember oxygen is 2 times 16, right? I actually forgot what that number is. I'm getting old, right? So that's 45 divided by 2 times 16. We got 1.41, right? So that was 1.41 moles. So we can actually answer the question here and say, well, what is the limiting reagent? So the limiting reagent in this case would have to be oxygen. All right? And why is that? Because it gives us less moles. We would like to produce more, but it means that we are going to run out of oxygen first, and the amount of oxygen that is there can only produce, in this case, just 1 mole of carbon dioxide. So that means that, therefore, the number of moles of carbon dioxide, as I did say to you, all we simply do, once we've identified our limiting reagent, right, we work out the number of moles, then we go to our formula. This is where I was showing you that, that method. We first convert to moles, we use our ratio. So our ratio says for every 17 moles of oxygen, right, we will get 12 moles of carbon dioxide. And so for how many moles? So if I've got 1.41 moles of oxygen, right, then how many moles of carbon dioxide are we going to obtain? And what we did, ladies and gents, was to cross multiply, and we said, well, 17n, right, 17 multiplied by n will give us 17n, right, 1.41 times 12, we got, okay, so that's multiplied by 12, okay, we got that 16.88, that's divided by 17, ladies and gents, and we found the number of moles of carbon dioxide that would be produced in this case would be equal to, okay, let's divide that by 17, and we said that's 0.99, or we can just round that off to just 1 mole. All right, so that's what we obtain, ladies and gents, right? All right, now that we found out the number of moles of carbon dioxide, that means that methane, or rather, hexane is actually the one that is in excess. Now, please, I want you to listen very carefully. So remember, the one that is the limiting reagent, and which one is the limiting reagent? It is the amount of oxygen. So the oxygen will actually determine how much of the hexane we are going to use, right? Because it means that we're not going to use up all of the hexane that we have, right? So firstly, how many number of moles did we have, right? We had, all right, so for hexane, that's mass divided by molar mass, we had 35 grams divided by, remember, we said the amount of moles of hexane in this case, or the molar mass, we said 6 times carbon, which is 6 times 12, plus 1 times 10, that's for hydrogen, right? There are 10 hydrogen atoms, right? And in this case, we've got the molar mass for hydrogen is 1. And so what did we obtain there, ladies and gents? So we said, well, that's going to be 35 divided by, I know we're repeating this again, so this would be 6 multiplied by 12 plus 1 times 10. So what we get there is 0.4, let's say 0.43, right? That's what we got. So these are the initial moles of hexane, right? But how many of them do we actually use, right? So we are now going to use our number of moles, our limiting reagent, to determine the amount of moles of hexane that are used. So what is our limiting reagent? Our limiting reagent is oxygen. So I'm going to say, well, for every 2 moles of hexane, C6, right, H10, we will get 17 moles of oxygen, right? I am trying to find out, in this case, how many moles of hexane we are actually going to use, right? So for 2 moles, we get, or rather we use 17 of oxygen. So for how many moles in this case, right? How many moles are we going to use of hexane, right? In this case, remember the number of moles of our limiting reagent is, where is it? 1.41, right? So for how many moles of hexane are we going to utilize all of the 1.41 moles of oxygen, right? So now, again, cross multiply 17 times n, that's 17n, and that's 2 times 1.41, that would give us 2.82. So we're going to divide that by 17, ladies and gents, right? And in this case, we say 2.82 divided by 17, okay? And that would give us the number of moles that we used, or that we are going to use for hexane, would be 0.17, right? So these are 0.17 moles. All right, ladies and gents, now we need to answer the questions. How many moles will be left unused? How many moles are in excess? How many are left over, right? Now we say the number of moles in excess would be determined by the number of moles that we have initial, right? The initial moles minus the number of moles that we use. So ladies and gents, how many did we start with? For hexane, we started with, now remember we found the number of moles to be 0.43. So that's what's given to us, right? Minus the ones that we use. How many did we use? We're going to use 0.17 because that's how much the oxygen allows us to use, right? The limiting reagent. So that's minus 0.17. So the number of moles that we've got in this case would be 0.43 minus 0.17, 0.17, okay? And so that means that the excess moles would be 0.26 moles. And of course, if they wanted us to convert that to mass, we would be able to do that quite well, right? Now, on the next question, they want us to calculate the percentage yield. I'll leave that for next time, right? But in terms of how we actually calculate the limiting reagent, that's how we're going to do it, ladies and gents, right? Now, let me quickly recap. We said, firstly, I found out what is the limiting reagent, okay? I said it is the one that's going to give me the smallest number of moles, right? The smallest number of moles of the product. The smallest moles in terms of our product. Okay, that is the one that limits the extent of the reaction. And what this simply means, ladies and gents, is that it means the limiting reagent is the agent that runs out first. It means this is the one that's going to stop the reaction from continuing. Why? Because it has actually ran out. Okay? And when we found out, in this case, the limiting reagent then will determine the number of moles of the products that we got by using our ratios, right? So once you've determined the limiting reagent, you use it to determine the moles of the product, but it also helped us to determine the number of moles of the reactants that were used, right? So the reactants used, okay? And as a result, once we get the reactants used, we compare it with the initial reactants, right? So we said initial reactants, right? And remember, this is in moles, okay, minus the ones that are used, and that will give us the excess moles. Ladies and gents, I hope that this has been helpful, and we will do more of these exercises. I'll take some past exam questions, but we'll do that again next time. So from me for now, I will see you guys again next time, and we will keep continuing with chemistry, right? As I did say, I am going to make chemistry fun for us, okay? But for now, I'll see you guys next time. Sharp, sharp.